Okay. So, okay, let's consider the probability, okay, like with two different factors, okay, two different factors. So, you know, which is a conjunction of two outcomes. So, for example, the probability of being dealt a card that is both a queen and a heart. Okay, so there are two possible outcomes. Okay, and but this is easy, right? Because I mean the card has only 52 outcomes, and you know the queen, the you know the rank of a card and the type of cards. I mean you know are relatively fixed. So that's the simple case. Let's consider a more complicated case. Okay, so this is like the proportions of combinations of hair color and eye color. Okay, and we consider black, brunette, red, and brown hair color. For eye color, we consider brown, blue, hazel, and green. Okay, so this is actually a data collected in 1974, okay, by social scientists, okay, and obviously this data was collected in Western country, okay, because you can see that, you know, there are more people in, you know, in brunette, red, and brown than people in black hair. Okay, and also, for example, for eye color, I mean, you may wonder like, how come we don't have like a black eye? Okay, but okay, what is our eye color? I mean, for like Asian people, what is our eye color? Black? No. Okay, I mean, in Chinese we always say, oh, I mean, 黑眼珠, okay, black eyeball, okay, black eye. I mean, but anyway, but I mean, in reality, actually, if you check the literature, okay, they will say we Asian people have brown eye, okay, 棕色眼睛. If you look at the mirror, you'll see you have a brown eye. Actually, it's scary to consider somebody has the eye color is black, totally black. That looks like a ghost, you know. Okay, actually, okay, if you use the term black eye, that has different meaning in English. So, you know, what does that mean by black eye? Okay, I mean, well, a little bit of English here, okay? So if somebody punch you in your face and you have like a, you know, you are black here, that's, we normally call that black eye. Okay, so we are never black eye, okay? Don't use black eye to describe your eye color to Western people because they will think, oh, you are just beaten by somebody? You know, so be careful, okay? But anyway, okay, we Asian people have brown eyes, okay, not black eyes, by the way, okay? So anyway, here we consider hair color and eye colors, okay? So this shows the proportion for the population, okay? I believe, well, it doesn't, does it say anything about, yeah, it doesn't say the whole, I mean, the whole population in this study, okay, it doesn't show here. But at least here, it shows like the proportion of the people with different hair color and eye color, okay, combined hair color and eye color, okay. So, so this is obviously much more complicated than the car example, right? Poker card example, because poker card, well, everything is fixed. But here, like, it's much more complicated. So in each cell, the table indicates the joint probability. Okay, because we are going to use this example to talk about some important concepts. So the first one is joint probability. Okay, of particular combinations of eye color and hair color, obviously. Okay, so if you have two outcomes, their joint probability. Okay, I mean, we can consider their joint probability, and we may be interested in the probabilities of the eye colors overall collapse across hair colors. Okay, so these probabilities are indicated in the right margin of the table. Okay, so therefore we call them marginal probability. So, so for example, we consider, for example, like a brown eye color across different hair colors. Okay, so you can see it's going to be displayed here. Okay, basically this one is like the summation of all these numbers, which is displayed here at the margin of the table. So it is why it is called marginal probability. Okay, so in this study, okay, 37% of the people have brown eyes. Okay, and 36% of people have like blue eyes. 16% of people have hazel eyes, and 11% of people have green eyes. So of course, if you add them up, it's going to be 1. Same thing. Okay, if you consider, for example, black hair across different eye color, then 18% of the people have black hair. Okay, and so on. Okay, so this one is also a marginal probability. Okay, and obviously, if you add up all these numbers, it's also 1. So we have. So if attributes are discrete, in this case, okay, in the case that we just discussed, like the hair color and the eye color, they are discrete, right? So the PE, okay, probability of certain eye color is the summation of the PEH. This PEH is like we consider all the joint probability with this eye color, across different hair colors. In this case, the hair colors, I mean, different hair colors are considered, and we add up all the joint probability to get the marginal probability of this particular eye color. Okay, the same thing can be said for hair color. The probability of a certain hair color, okay, is something like this. So if attributes are continuous, then we need to change this PR equal to this one. PRC DC. Okay, I'm sorry. This DC should be put at the end. And the PC should be integral PRC DR, where DR should be put at the end. You get the idea, okay? Shouldn't be too difficult to understand, right? Okay? So, the probability of one outcome, given that we know another outcome is true, is called conditional probability, right? I mean, previously we just keep saying conditional probability, but we didn't really give the formula for that, right? Okay, I keep telling you we are going to use conditional probability. We are going to use Bayes rule, but yeah, Bayes rule obviously is for conditional probability, but yeah, now it's a good time to talk about probability, conditional probability. For example, conditional on that the person has blue eyes, the probability that the person has brown hair. What is the probability the person has brown hair? So total amount of blue-eye people is 36%, 0.36. Blue eyes. Okay, the marginal probability is 36, 0.36. Okay, 36% of the population has blue eye. And among these 36%, okay, we want to see what is the probability or what is the portion of the people to have brown hair. So the people to have brown hair, out of these 36%, 0.16, okay, in this 0.36, okay, have brown hair. Okay, so the conditional probability is going to be 0.16 divided by 0.36 is going to be 45%. So 45% has brown hair, okay, given that the person has blue eyes. So this is very important. Why? Okay, because, okay, if you don't know, if you do not know anything, okay, remember remember the example I just mentioned, what is the probability that it's cloudy here in Zhongli? And then I said, what is the probability that if it's sunny, what is the probability that it's clouded? We talked about this, remember, at the beginning of the class today, right? Okay, so, okay, same thing. The general probability of having brown hair is 0.21 here. If you only consider, okay, if you, at random, you pick up anyone, okay, the chance for that person to have brown hair is 21%, right? 0.21. But once you realize that that person has blue eyes, once you realize that person has blue eyes, the chance, okay, the chance of that person to have brown hair, okay, increases to 0.45, right? To increase from 0.21 to 0.45, this is relocation of probability, right? Right? So this is Bayesian inference. This is Bayesian inference. Okay. The thing that here, okay, we do everything by calculation, right? We obtain everything by calculation, right? From that table, okay, we get that 0.45, we get that 0.21, we get that 0. All these numbers are obtained from the computations, right? So now, okay, this relocation of credibility, okay, can be done mathematically. Okay. So let's consider this computation of conditional probability. Okay. The notation of conditional probability is PH over E, right? Given a particular eye color, the chance of that a particular hair color. Okay. Okay, this one is PHE stands for PEH, the joint probability, divided by P of E, right? Right? Hopefully, this is, and from the PE previous discussion, we know, okay, the PE can be written like this, right? Summation H PEH, right? Okay. In high school, when you learn Bayes rule, okay, this is the base rule. Okay, but you know, and this shows the conditional probability of, for example, if you know that person has blue eye, what is the chance for that person to have black hair? Is 0.08. The chance for that person to have brunette hair is 0.39. The chance for that person to have red hair is 0.08. And the chance for that person to have blonde hair is 0.45. So you can do all this conditional probability given blue eye. Okay, is like that. And the chance for, you know, blue eye. Given a blue eye person, okay, the chance for all different hair colors obviously is 1, right? Which is the sum of all this conditional probability. That's obviously the case, right? And you see here, basically this one, the denominator. Okay, for example, if we want to remember, originally we are discussing this one, right? The 0.16 is a joint probability, and 0.36 is the marginal probability that that person has blue eye, right? Okay, which is this one. Okay. And if the attributes are discrete, that's what we have. Okay? We just discussed that. When the attributes are continuous, then we need to change our formula into this one. The only difference is that this one is this denominator. Okay? Where, this DC should be put at the back, but you get the idea. Okay? So it's important to recognize that in general, PR on condition of C is not equal to PC on condition of R, because you can, obviously write the formula. The denominator will be the same. Both are joint probability PRC. The issue is the denominator. The denominator will be different. Right? Right? Okay. So when we say the probability of X given Y, we do not mean that Y has already happened and X has yet to happen. This doesn't mean the causality. Okay. If you say Y has already happened, and what is the probability for X to happen, this is more like we are describing a causality, like kind of like a chance that Y causing X. Okay, but no. Okay, all it means is just that we are restricting our calculations of probability to particular subset of possible outcomes. Okay? So a better growth of Px on condition Y is, a better description is among all joint outcomes with value Y, the probability of them, also has the value X. Okay? So this is a better description. It has nothing to do with causality. Oh, by the way, if you guys are interested in causality, there's a book that is very famous. I would really recommend you guys reading. Okay, it's the book. The title of the book is called "The Book of Why." I don't know if you have heard of this book, "The Book of Why." Okay, the author is first. The Book of Why is not what should I say? It's more like for popular for regular population. It's not for like okay, just for engineer or for like somebody who has to master like mathematics. No. It's more like for general population. It is a science book for sure. Okay, but it's more like a popular science book. Okay, the book of why. I mean, the author is actually a Turing Award winner. Okay, Julia Peer. Okay, he actually derived like all the causality theory. Okay, and because of that contribution, he won the Turing Award about 20 years ago. Okay, he's a professor at computer science professor at the UCLA. Okay, very very famous, and I believe like you can find translation of that book. Okay, from bookstore as well. I do think like that book also help you to understand some AI knowledge, because you know you can also use causality theory to explain AI. Okay, so that book is a very very good book. Okay, I highly recommend. Okay, anyway, but the Bayesian is not necessarily about causality. Okay, Bayesian is much older. Okay, because it comes from like statistics. So let's consider this example. This example is a more complete example. Okay, consider trying to diagnose a rare disease. Okay, rare disease. Okay, suppose that in the general population, the probability of having the disease is only 1 in 1,000. Okay, so so probability of a person having disease is 0.001, right? 0.001. Okay, because 1 in 1,000. So we denote the true presence or absence of the disease as a value of parameter theta. So we say theta equal to this crying face if the disease is present in a person. So the first sentence, okay, actually means like right? In other words, obviously, the probability for a person not having disease is what? 0.999, right? Get it? Okay. So, where is it? Okay. So the base rate of the disease is therefore this one is okay. I already wrote it. This is our prior belief that a person selected at the random has the disease. Okay. So suppose that there is a test for the disease. Okay. So remember, like, we are in a COVID-19 era, right? So we know test kit, a rapid test kit, very, very well, right? A lot of you may already tried it many times anyway, okay? So anyway, so this test kit has a 99% hit rate. What is 99% hit rate? 99% hit rate means like if a person has the disease, then the test result is positive 99% of the time. This is pretty good, okay? Actually, like the COVID-19 test kit that we have, like I don't think they have the hit rate is so high. So let's say like the test positive, let's just use a plus sign to indicate positive, okay? So that means what? The probability, if somebody has the disease and the test result is positive, okay? So on the condition that person already has the disease, the conditional probability, okay, that person tests positive is the 0.99, right? Right? So it's going to be something like that, right? This one. Okay? And also, that we know that the test has a false positive rate of 5%. What is false positive rate? So it means when the person is healthy, if the person is healthy, the test result may show he has a disease. That's a false alarm, right? So in the condition, under the condition that the person is healthy, the result come up positive under this condition is 5%, right? So 0.05. Right? So it's this one. Okay? So our question is, suppose we sample a person at random from the population, which is randomly get somebody and run the test on that person, okay, administer the test, and it comes up positive. What is the posterior probability that the person has disease? So we are looking for the probability, this one. P, okay, now we know that person is positive, right? So we know that result is positive. What is the probability that person really has disease, right? We want to know on the condition the test result is positive. Okay, that person really, under this condition, that person really has the disease. What is the probability? We want to know this one. Right? So based on this, can you compute this one? Okay. Actually, you could do, what you can do is that you can construct a table, something similar to this one, something similar to this one, but in a much easier format, because okay, one side indicate the person has that particular rare disease or not. The other side indicate that person tests positive or not. So each side you only have like two possible outcome. So the table only has like four joint probabilities, right? Okay, so let's okay. So it's something like this. Well, this one is running out of ink. So and we also have marginal probability. So this one indicate a test. This one indicate the illness or disease. Okay, so we have like a happy face. We have like a crying face. And this one is a positive, negative. Okay? And first, we know like from the first one, okay, we know this one is the marginal probability is 0.001, right? And this one is 0.999, right? Right? And then, okay, if this one is 0.99, okay, this one is what? What is this one? This one is like this one is P crying face and the P positive and crying face, right? Joint probability of this, right? So based on, because we already know the crying face, right? P crying face, we already know that, right? This is 0.001, right? So based on 0.001, the 0.99, we can get this joint probability, right? Right? This is a plus and a crying face. Plus and the crying face. So this one, we get this one. Okay? So if you get this one, you also get this one, right? Because 0.001 minus this one is this one, right? Okay, so we get this one. And then look at here. This one, what is this one? This one is probability of happy face as a denominator, and the probability of plus and the happy face, right? The joint probability of plus and happy face as a denominator. And we already know the probability of happy face, right? Which is 0.999, right? And if you know this one, then you know the joint probability of plus and the happy face. So plus and happy face. So you know this one, right? If you know this one, and because we already know this, the marginal probability, this one, so we know this one as well. So if you know these two, you can compute this one, right? Right? So it shouldn't be too difficult, right? Right? So actually, it's exactly just like what I said, okay? You can compute this one. You can compute, yeah. You can compute all these things. And then after that, after you do that, okay, you try to compute this one. This one. This is the one that we are interested in. This is what? This is probability of plus. Okay. On top is probabilities of plus and crying face. The joint probability of plus and the crying face. So probability of plus is here, this one. And the probability, this is denominator. And probability of plus and crime phase is this one. This is your denominator. This is your numerator. Okay, so it's going to be this one divide. Is it? Am I? No. Yeah, I think I draw the column and the row differently than this one, but you get the idea. Okay, you get the idea. So the answer is 0.019. So let me repeat. Remember I just told you that this rapid test kit is pretty darn good, right? Because, well, just like our description, okay, this rapid test kit, okay, the hit rate is 99%, and the false alarm rate is 5%. This is pretty good, okay? I don't think any COVID-19 rapid test kit is as good as this one, okay? So, even with this such a good rapid test kit, okay, and if you try to use it on a person at random, and when it comes up positive, the chance for that person to have disease is only, well, close to 2%. That's very low, right? That's very low, right? You may feel it's against your intuition. You say, oh, this person tests positive. How come the chance for that person to have like disease is only like less than 2%? Why? There are a few things I can describe. I can discuss with you here. Okay. The first thing is like this. Okay. What is the person to have disease at random? What is the probability that a person has disease at random? The person to have disease at random is this one, right? 1 out of 1,000 people, right? So the original probability is 0.001. Now the probability becomes 0.019. The difference is how much? The probability increased 19 times, right? From this situation, from the chance that person at random to have a disease. It's already 19 times higher. So yeah, that test kit works. That test kit works. But the issue is that, okay, because this is a rare disease. Okay, this is a rare disease. So if it's a rare disease, I mean, well, I mean, it's just not going to, have like a the chance for, even if that person tests positive, it's just not going to be very likely that person has disease. It's just like increase that probability. So normally, okay, when you have this test kit, okay, in mathematics, in like a medical field, okay, how do they use this rapid test kit? They normally actually only use rapid test kit in 2 situations. Okay, the first situation is that, okay, well, the disease is rare, okay, but you already have certain symptoms of that disease. And then we try to use the rapid test kit on you to see, okay, if that, if that's the case. Okay, so the person is not a random person. That person already has certain symptoms from that disease. Okay, let me use a COVID-19, but COVID-19 is probably not a good example now because COVID-19 is no longer a rare disease, right? Okay. Okay, let me use the AI, AIDS. Okay, AIDS. I'm not against like a homosex. Okay, first time disclaimer. Okay, I'm just talking about like a particular disease. Okay, by the way, AIDS can be spread like even across like gender. Anyway, so anyway, AIDS is still considered rare disease, right? I mean, but if somebody already exhibit certain symptoms from, of the AIDS, for example, like because AIDS like is the disease that you are gradually losing the defense to the attack of the outside like bacteria. So if the doctors think, well, this guy is very easy to get infected by many issues, so the doctor will start to suspect that this person may have AIDS. So in that case, the chance for that person to have the AIDS is no longer 0.001. The chance for that person to have the AIDS may be like 0.01. Okay, maybe 1/100. Okay, or even like maybe 1 over like 2 out of 100 maybe. So when the doctor used the test kit with such a capability over that patient and it come up positive, well then the chance, say original is 2%, is 0.02. Now this probably will be increased by 19 times, so it becomes what, 38%. Well, now the test kit is very helpful, right? Right? Because when the test kit show up positive, yeah, it's close to like 40% that this person has that disease, right? So that's the first thing. Okay, the first situation that the doctor has to observe certain symptoms and then use the test kit. Another situation is what? Is the situation when like COVID-19, it's no longer a rare disease. For example, in Taiwan, like COVID-19, I think it's maybe 30 to 40%, of population that already carry like a COVID-19, virus. So in that case, the rapid test kit helps. Of course, even the rapid test kit is not as effective as the one that we described here. If it can increase the probability by twice, then as I said, if it's 10%, then increase by maybe twice, then it's 20%. So it's still quite useful, right? And this also answered one question. Remember, a few years, not few years, I think probably a little bit more than a year ago, right? When Taiwan doesn't have so many COVID-19 cases. Remember, in legislation 院，在立法院, some people just keep asking the government to run a big test over a large area to see what is to find out all the people who have COVID-19. But at that time, in Taiwan, COVID-19 is considered rare disease, right? Okay, so based on this, you can understand. Even if we have a very effective rapid test kit, the chance for somebody who really doesn't have disease, but I mean, the test positive, and I mean, it's actually very high, right? Okay, I mean, the you know, when it tests like a positive and that person really have the disease, it's only 2%. And not to mention, like, I mean, in other words, when the test come out positive, that person doesn't have disease, it's 98%. Okay, so you want to, you know, put all these people in quarantine? Okay, that sounds like strange, right? So that's the reason, that's the rationale why the government agency doesn't want to do that back to like probably more than a year ago. Okay, so the situation now is different, but the situation because now the COVID-19 is no longer a rare disease. So this example, I just want to use this example to show you, okay, the concept of Bayesian inference, and it happened to have a connection to our, what should I say, to the COVID-19, which is like the disease that we are facing, like nowadays. Okay. So I guess we're running out of time today, so we'll stop here today. Okay. So next time we'll start from like here. Okay. Any question? If no question, let's call it a day. Okay, I will see you guys next week. Okay, I think I will.